Of shortest paths. This is the finale. Hopefully it was worth waiting for. Reminder, there's a quiz coming up soon. You should be studying for it. There's no problem set due at the same time as the quiz because you should be studying now. It's a take-home exam. It's required that you come to class on Monday. Of course, you'll all come. But everyone watching at home should also come next Monday to get the quiz. It's the required lecture. All right. So we need a bit of a recap in the trilogy so far. So the last two lectures, the first two episodes, were about single source shortest paths. So we wanted to find the shortest path from a source vertex to every other vertex. And we saw we saw a few algorithms for this. Here's some recap. We saw in the unweighted case, that was sort of the easiest, where all the edge weights were 1. Then we could use breadth first search. And this costs what we call linear time in the graph world. Number of vertices plus number of edges. Next simplest case, perhaps, is non-negative edge weights. And in that case, what algorithm do we use? Dijkstra. All right, everyone's awake. Several answers at once. Great. Okay, so this takes almost linear time if you use a good heap structure. So V log V plus E. And in the general case, general weights, we would use Bellman-Ford, which we just saw. And that costs VE. Good. Okay, which is quite a bit worse. This is, ignoring log factors, Dijkstra is basically linear time. Bellman-Ford is at least quadratic if you have a connected graph. So in the sparse case, when E is order V, this is about linear, this is about quadratic. In the dense case, when E is about V squared, this is quadratic, and this is cubic. So Dijkstra and Bellman-Ford are separated by about a linear factor. Just an order V factor, which is pretty bad. Okay? But that's the best we know how to do for single source shortest paths. Negative edge weights, Bellman-Ford is the best. We also saw in recitation the case of a DAG. And there, what do? Topological sort, yeah. So you can do topological sort to get an ordering on the vertices. Then you run Bellman-Ford one round. This is one way to think of what's going on. You run Bellman-Ford in the order given by the topological sort just once, and you get a linear time algorithm. So a DAG is another case where we know how to do well even with weights. Unweighted, we can also do linear time. Most of the time, though, will be... So you should keep these in mind in the quiz when you get a shortest paths problem, or what you end up determining is the shortest paths problem. Think about what's the best algorithm you can use in that case. Okay, so that's single source shortest paths. And so in our evolution of the Death Star, initially it was just non-negative edge weights, then we got negative edge weights. Today, the Death Star challenges us with all pairs shortest paths, where we want to know the shortest path weight between every pair of vertices. Okay, so let's get some quick results. What can we do in this case? So, for example, Suppose I have an unweighted graph. Any suggestions on how I should compute all pairs shortest paths? So between every pair of vertices, I want to know the shortest path weight. BFS. Couple more words. Yeah?
You do V times V one structure.
Right, BFS V times. Okay, I'll say V times BFS. Okay, so the running time would be V squared plus V times E, yep, which is, assuming your graph is connected, V times E. Okay, good. That's probably about the best algorithm we know for unweighted graphs. So a lot of these are going to sort of be the obvious answer. You take your single source algorithm, you run it V times, that's the best you can do. Okay, or the best we know how to do. This is not so bad. This is like one iteration of Bellman-Ford for comparison. We definitely need at least like V squared time because the size of the output is V squared. It's V squared shortest path weights we have to compute. So this is not perfect, but pretty good. And we're not going to improve on that. So non-negative edge weights, the natural thing to do is to run Dijkstra V times. Okay, no big surprise. And the running time of that is, well, V times E again, plus V squared log V. Which is also not too bad. I mean, it's basically the same as running BFS. And then there's this log factor. If you ignore the log factor, this is the dominant term. And I mean, this had an additive V squared as well. So these are both pretty good. I mean, this is kind of neat that with essentially the time it takes to run one Bellman-Ford plus a log factor, you can compute all pairs shortest paths if you have non-negative edge weights. So, I mean, comparing all pairs to single source, this seems a lot better, okay, except we can only handle non-negative edge weights. Okay, so now let's think about the general case. Well, this is the focus of today, and here's where we can actually make improvement. So the obvious thing is V times Bellman-Ford. Which would cost V squared times E. And that's pretty pitiful, and we're going to try to improve that to something closer to the non-negative edge weight bound. So it turns out here we can actually make improvement, whereas in these special cases we really can't do much better. Okay, I don't have a good intuition why, but it's the case. And so we'll cover something like 3 algorithms today for this problem. The last one will be the best, but along the way we'll see some nice connections between shortest paths and dynamic programming, which we haven't really seen yet. We've seen shortest paths and applying greedy algorithms to it, but today we'll actually do dynamic programming. The intuition is that with all pairs shortest paths, there's more potential subproblem reuse. We've got to compute the shortest path from x to y for all x and y. Maybe we can reuse those shortest paths in computing other shortest paths. Okay, there's a bit more reusability, let's say. Okay, let me quickly define all pairs shortest paths formally. You have, because we're going to change our notation slightly. It's because we care about all pairs. So as usual, the input is a directed graph, some vertices and edges. We're going to say that the vertices are labeled 1 to n. For convenience, because we're going to think of things more with all pairs, we're going to think of things more as an n by n matrix instead of edges in some sense, because it doesn't help to think anymore in terms of adjacency lists. And you have edge weights as usual. This is what makes it interesting. Some of them are going to be negative. So W maps every edge to a real number. And the target output is the shortest path matrix. So this is now an n by n matrix. So n is just the number of vertices of shortest path weights. So delta of I comma j is the shortest path weight from I to j for all pairs of vertices. So this you could represent as an n by n matrix in particular. Okay, so now let's start doing algorithms. So we have this very simple algorithm, v times Bellman-Ford, v squared times e, and just for comparison sake, I'm going to say, let me rewrite that, v times Bellman-Ford. So that's this running time of v squared e, and I'm going to think about the case where, let's just say that the graph is dense, meaning that the number of edges is quadratic and the number of vertices. So in that case, this will take v to the fourth time, which is pretty slow. We'd like to do better. So first goal will just be to beat v to the fourth. V hypercubed, I guess. Okay, and we're going to use dynamic programming to do that. Or at least that's where the motivation will come from. It'll take us a while before we can even beat v to the fourth, which is maybe a bit pathetic, but it takes some clever insights, let's say. Okay, so I'm going to introduce a bit more notation for this graph. So I'm going to think about the weighted adjacency matrix. So I don't think we've really seen this in lecture before, although I think it's in the appendix. What that means, so normally adjacency matrix is like 1 if there's an edge and 0 if there isn't. And this is in a digraph, so you have to be a little bit careful. Here, these values, the entries in the matrix, are going to be the weights of the edges. Okay, this is if ij is an edge. So if ij is an edge in the graph, and it's going to be infinity if there is no edge. Okay, this is a more, in terms of shortest paths, this is a more useful way to represent the graph, right? So this encodes everything that we need from here. And now we just have to think about it as a matrix. And matrices will be a useful tool in a little while. Okay, so now I'm going to define some subproblems. And there's different ways that you could define what's going on in the shortest paths problem. Okay, the natural thing is I want to go from vertex I to vertex j. What's the shortest path? Okay, we need to refine the subproblems a little bit more than that. Not surprising. And if you think about, by analogy to Bellman-Ford, what Bellman-Ford does is it tries to build longer and longer shortest paths. But here length is in terms of the number of edges. So first it builds shortest paths of length 1. We prove in the first round it does that. The second round it provides all shortest paths of length 2, of hop count 2, and so on. We'd like to do that sort of analogously and try to reuse things a little bit more. So I'm going to say d sub ij superscript m is the weight of a shortest path from I to j with some restriction involving m. So shortest path from I to j, so using at most m edges. Okay, for example, if m is 0, then we don't have to really think very hard to find all shortest paths of length 0. Okay, they use 0 edges, I should say. And so Bellman-Ford sort of tells us how to go from m to m plus 1. So let's just figure that out. So one thing we know from the Bellman-Ford analysis is if we look at Dij superscript n minus 1, we know that in some sense the longest shortest path of relevance, unless you have negative weight cycles, the longest shortest path of relevance is when m equals n minus 1, because that's the longest simple path you can have. So this should be the shortest path weight from I to j, and it would be no matter what larger value you put in the superscript. This should be delta of I comma j if there's no negative weight cycles. Okay, so this feels good for dynamic programming. This will give us the answer. If we can compute this for all m, then we'll have the shortest path weights in particular. We need a way to detect negative weight cycles, but let's not worry about that too much for now. There are negative weights, but let's just assume for now there's no negative weight cycles. Okay, and we get a recursion, recurrence. So, and the base case is when m equals 0. This is pretty easy. If you have the same vertices, the weight is 0, and otherwise it's infinity. Okay, and then the actual recursion is for m. Okay, so I got this right. This is a pretty intuitive recursion for Dij of m is a min of smaller things in terms of m minus 1. I'll just draw the picture, and then the proof of that claim should be obvious. So this is proof by picture. So we have, on the one hand, I over here, and j over here. We want to know the shortest path from I to j. And we want to use at most m edges. So the idea is, well, you could use m minus 1 edges to get somewhere. So this is at most m minus 1 edges. Some other place, and we'll call it k. So this is a candidate for k. And then you could take the edge directly from k to j. So this costs a kj, and this costs d I k m minus 1. Okay, and that's a candidate path of length that uses at most m edges from I to j, and this is essentially just considering all of them. Okay, so there's sort of many paths we're considering. All of these are candidate values of k. We look at all, we're taking them in over all k as intermediate nodes, whatever. So there they are. We take the best such path. That should encompass all shortest paths, and this is essentially this is sort of what Bellman-Ford is doing, although not exactly. We also sort of want to think about, well, what if I just go directly with, say, m minus 1 edges? What if there is no edge here that I want to use in some sense? Well, we always think about there being, and the way that the A's are defined, there's always this zero weight edge to yourself. So you could just take a path that's shorter, go from di to j, and j is a particular value of k we might consider, and then take a zero weight edge at the end from a jj. Okay, so this really encompasses everything, and so that's a pretty trivial claim. Clear? Okay, now once we have such a recursion, we get a dynamic program. I mean, this is it in some sense. It's written recursively. You can write it bottom up. And I would like to write it bottom up a little bit because while it doesn't look like it, this is a relaxation. This is yet another relaxation algorithm. So I'll give you, so this is sort of the algorithm. This is not a very interesting algorithm, so you don't have to write it all down if you don't feel like it. It's probably not even in the book. This is just an intermediate step. So we loop over all m. That's sort of the outermost thing to do. Want to build longer and longer paths. And this vaguely corresponds to Bellman-Ford, although it's actually worse than Bellman-Ford. Hey, what the heck? It's a stepping stone. Okay, then for all I and j, And then we want to compute this min. So we'll just loop over all k. And relax. And here's where we're actually computing the min. And it's a relaxation, is the point. This is our good friend, the relaxation step. Relaxing edge, well, it's not, yeah. I guess we're relaxing edge kj or something. Except it's a little bit, we don't have the same clear notion. I mean, it's a particular thing that we're relaxing. It's not just a single edge, because we don't have a single source anymore. It's now relative to source I, we are relaxing the edge kj, something like that. But this is clearly a relaxation. We're just making the triangle inequality true if it wasn't before. Triangle inequality's got to hold between all pairs. And that's just implementing this min, right? You're taking dij, you take the min of what it was before, in some sense. So that was one of the possibilities we considered when we looked at this zero-weight edge. We say, well, or you could go from I to some k in some way that we knew how to before, and then add on the edge. And this is, and check whether that's better. If it's better, set our current estimate to that. And you do this for all k. In particular, you might actually compute something smaller than this min, because I didn't put superscripts up here. But that's just making PAS even better. Okay, so you have to argue that relaxation is always a good thing to do. So by not putting superscripts, maybe I do some more relaxation, but more relaxation never hurts us. Okay, you can still argue correctness using this claim. It's not quite the direct implementation, but there you go. Dynamic programming algorithm. The main reason I write it down, so you see that it's a relaxation, and you see the running time is n to the fourth. Okay, which is certainly no better than Bellman-Ford. Bellman-Ford was n to the fourth even in the dense case, and it's a little better in the sparse case. So not doing so great, but it's a start. Okay, gets our dynamic programming minds thinking. And we'll get a better dynamic program in a moment. But first, there's actually something useful we can do with this formulation. And I guess I'll ask, but I'll be really impressed if anyone can see. Does this formula look like anything else that you've seen in any context, mathematical or algorithmic? Have you seen that recurrence anywhere else? Okay, not exactly as stated, but similar. Yeah, I'm sure if you thought about it for a while, you could come up with it. Any answers? Okay, I didn't think it would be very intuitive, but the answer is matrix multiplication. And it may now be obvious to you, or it may not, but there you go. You have to think with the right quirky mind. Then it's obvious that it's matrix multiplication. But remember, matrix multiplication, we have A, B, and C. They're all n by n matrices. And we want to compute C equals A times B. And what that meant was, well, Cij was a sum over all k of Aik times Bkj. Right, that was our definition of matrix multiplication. And that formula looks kind of like this one. I mean, notice the subscripts, Ik and Kj. Now, the operators are a little different. Here we're multiplying the inside things and adding them all together. There we're adding the inside things and taking them in. But other than that, it's the same. Yeah. Okay, weird, but here we go. So the connection to shortest paths is you replace these operators. So let's take matrix multiplication and replace What should I do first? Plus this thing with min. So why not just change the operators? Replace dot with plus. You know, this is just a different algebra to work in where plus actually means min and dot actually means plus. So you have to check that things sort of work out in that context. But if we do that, then we get that Cij is the min over all k of aik plus, well, a bit messy here, plus bkj. And that looks like what we actually want to compute here. For one value of m, you have to sort of do this m times. But this conceptually is dij m, and this is dik m minus 1. So this is looking like a matrix product, which is kind of cool. So if we just sort of plug in this claim then, and think about things as matrices, so the claim, the recurrence, gives us that, and I'll just write this now in matrix form, that d to the m is d to the m minus 1, funny product A. Right, so these were the weights. These are the weighted adjacency matrix. This was the previous d value. This was the new d value. So I'll just rewrite that in matrix form with capital letters. Okay, I'm going to circle up things that are using this funny algebra. So in particular, circled product. Okay, so that's kind of nifty. We know something about computing matrix multiplications. We can do it in n cubed time. For a bit fancier, maybe we can do it in subcubic time. So we could try to sort of use this connection. And, well, think about what we're computing here. Right? We're saying, well, d to the m is the previous one times a. So does that, what is d to the m? Is that some other algebraic notion that we know? Yeah, it's the exponent. We're taking a and we want to raise it to the power m with this funny notion of product. So in other words, d to the m is really just a to the m in a funny way. So I'll circle it. Okay. So that sounds good. We also know how to compute powers of things relatively quickly, if you remember how. Okay, I need to define, for this notion, this power notion to make sense, I should say what a to the 0 means. And so I need some kind of identity matrix. And for here, the identity matrix is this one. I get it right. So it has zeros along the diagonal and infinities everywhere else. Okay, that's sort of just to match this definition. Dij 0 should be zeros on the diagonals and infinity everywhere else. But you can check this as actually an identity. If you multiply it with this funny multiplication against any other matrix, you get the matrix back. Nothing changes. This really is a valid identity matrix. And I should mention that for a to the m to make sense, you really need that your product operation is associative. So I should a to the m circled makes sense because circled multiplication is associative, and you can check that. Not hard because min is associative and addition is associative and all sorts of good stuff. And you have some kind of distributivity property. And this is in turn because the real numbers with, and get the right order here, with min as your addition operation and plus as your multiplication operation is a closed semi-ring. So if ever you want to know when powers make sense, this is a good rule. If you have a closed semi-ring, then matrix products on that semi-ring will give you an associative operator, and then good, you can take products. Okay, that's just some formalism. So now we have some intuition. The question is, what's the right algorithm? There are many possible answers, some of which are right, some of which are not. So we have this connection to matrix products, and we have a connection to matrix powers. And we have algorithms for both. The question is, what should we do? So all we need to do now is to compute a to the funny power n minus 1. Right? N minus 1 is when we get shortest paths, assuming we have no negative weight cycles. In fact, we could compute a larger power than n minus 1. Once you get beyond n minus 1, multiplying by a doesn't change you anymore. So how should we do it? Okay, you're not giving any smart answers. I'll give the stupid answer. You could say, well, I take A, I multiply it by A, and then I multiply it by A, and I multiply it by A, and I use normal, boring matrix multiplication. So I do like n minus 2 standard matrix multiplies. So standard multiply costs like n cubed. And I'm doing like n of them. So this gives me an n to the 4th algorithm. So compute all the shortest path weights and n to the 4th. Woohoo! Okay, no improvement. So how could I do better? Right, natural thing to try, which sadly does not work, is to use a subcubic matrix multiply algorithm. We will in some sense get there in a moment with a somewhat simpler problem. But it's actually not known how to compute shortest paths using fast matrix multiplication, like Strass's algorithm. But good suggestion. Okay, you have to think about why it doesn't work. Yeah, I'll tell you, but it's not obvious, so it's a perfectly reasonable suggestion. But in this context, it doesn't quite work. It will come up in a few moments. The problem is Strassen requires the notion of subtraction. And here, addition is min. And there's no inverse to min. Once you've taken the arguments, you can't sort of undo a min. Okay, so there's no notion of subtraction, so it's not known how to pull that off, sadly. So what other tricks do we have up our sleeve? Yeah?
We have the divide and conquer log n powering.
Divide and conquer log n powering. Yeah, repeated squaring. That works. Good. We had a fancy way, if you had a number n, you sort of looked at the binary number representation of n, and you either squared the number or squared it and added another factor of a. Here, we don't even have to be smart about it. Okay, we can just compute. We really only have to think about powers of 2. What we want to know, and this is, I'm going to need a bigger font here because it's multiple levels of subscripts. A to the circled power 2 to the ceiling of log n. Well, actually, n minus 1 would be enough. Right, there you go. You can write n if you didn't leave yourself enough space like me. And the ceiling and the circle. Okay, this is funny thing. This just means the next power of 2 after n minus 1, 2 to the ceiling log. Right? So we don't have to go directly to n minus 1. We can go further, because anything farther than n minus 1 is still just the shortest path weights. If you look at the definition and you know that your paths are simple, which is true if you have no negative weight cycles, then fine, just go farther. Why not? And so to compute this, we just do ceiling of log n minus 1 products. Just take A, square it, and then take the result and square it. Take the result and square it. So this is order log n multiplies or squares. And we don't know how to use Strassen, but we can use the boring standard multiply of n cubed, and that gives us n cubed log n running time. Okay, which finally is something that beats Bellman-Ford in the dense case. Okay, when in the dense case, Bellman-Ford was n to the 4th. Here we get n cubed log n, finally something better. In the sparse case, it's about the same, maybe a little worse. E is order v. Then we're going to get like v cubed for Bellman-Ford. Here we get n cubed log n. Okay, up to log factors, this is an improvement some of the time. Okay, it's about the same the other times. Another nifty thing that you get for free out of this is you can detect negative weight cycles. So here's a bit of a puzzle. How would I detect, after I compute this product, a to the power 2 ceiling log n minus 1, how would I know if I found a negative weight cycle? What would that mean in this matrix of all pairwise shortest paths of at most a certain length? If I found a cycle, what would have to be in that matrix? Yeah.
Some paths will get shorter, so you compare.
Right. So I could, for example, take this thing, multiply it by A, see if the matrix changed at all. Right. That works fine. That's what we do in Bellman-Ford. It's an even simpler thing. It's already there. You don't have to multiply. But that's the same running time. That's a good answer. The diagonal would have a negative value. Yeah. So this is just a cute thing. Both approaches would work. Can detect a negative weight cycle just by looking at the diagonal of the matrix. You just look for a negative value in the diagonal. Okay. So that's algorithm 1, let's say. We've seen several that are all bad, but I'll call this number 1. Okay, we'll see 2 more. This is the only one that I shouldn't say that. Fine, there we go. So this was one dynamic program that wasn't so helpful, except it showed us a connection to matrix multiplication, which is interesting. We'll see why it's useful a little bit more. But it led to this nasty 4 nested loops. And if we're using this trick, we got down to n cubed log n. Let's try just for n cubed. Okay, just get rid of that log. It's annoying. Makes you a little bit worse than Bellman-Ford and the sparse case. So let's just try to just erase one of these nested loops. Okay, I want to do that. Okay, obviously that algorithm doesn't work because it refers to k and it's not defined, but I've got enough variables. Why don't I just define k to be m? Okay, turns out that works. Well, I'll do it from scratch, but why not, right? I don't know if that's how Floyd and Warshall came up with their algorithm, but here you go. Here's Floyd-Warshall. The idea is to define the subproblems a little bit more cleverly so that to compute one of these values, you don't have to take the min of n things. I just want to take the min of 2 things. If I could do that and I'd still only have n cubed subproblems, then I would have n cubed time. So the running time of a dynamic program is number of subproblems times the time to compute the recurrence for one subproblem. So here it's linear times n cubed, and we want n cubed times constant. That would be good. So that's Floyd-Warshall. So here's the way we're going to redefine Cij, or I guess there it was called Dij. Good. So we're going to define something new. So Cij superscript k is now going to be the weight of the shortest path from I to j as before. Notice I use the superscript k instead of m because I want k and m to be the same thing. Whoa, deep. Okay, now here's the new constraint. I want all intermediate vertices along the path, meaning all vertices except for I and j at the beginning and the end, to have small label. So they should be in the set from 1 up to k. And this is where we're really using that our vertices are labeled 1 up to n. So I'm going to say, well, first think about the shortest paths that don't use any other vertices. That's when k is like 0. Then think about all the shortest paths that maybe they use vertex 1. And then think about the shortest paths that maybe use vertex 1 and vertex 2. Right? Why not? You could define it in this way. Turns out, then when you increase k, you only have to think about one new vertex. Here we had to take a min over all k. Now we know which k to look at. Okay, maybe that makes sense. Maybe not quite obvious yet. But I'm going to redo this claim. Redo a recurrence. So Maybe first I should say some obvious things. So if I want delta of ij, I want the shortest path weight, well, just take all the vertices. So take Cij superscript n. That's everything. And this even works, this is true even if you have a negative weight cycle, although again, we're sort of going to ignore negative weight cycles as long as we can detect them. And another simple case is if you have, Cij to 0. Let me put that in the claim. Be a little bit more consistent here. So here's the new claim. If we want to compute Cij superscript 0, that is, what is it? Superscript 0 means I really shouldn't use any intermediate vertices. So this has a very simple answer, a 3-letter answer. So it's not 0. It's 4 letters. What's that? Nil. No, not working yet. Has some subscripts too. So the definition would be, what's the shortest path weight from I to j when you're not allowed to use any intermediate vertices? Sorry? Yeah, so it has a very simple name. That's the tricky part. Right, so if I equals j, you're clever. Right, open bracket I equals j means 1, well, okay. Sort of works, but it's not quite right. In fact, I want infinity if I does not equal j, and I want 0 if I equals j. Aij. Good. I think it's Aij. Should be, right? Maybe I'm wrong. Right, Aij. So it's actually not what I said. That's the point. If I does not equal j, you still have to think about a single edge connecting I to j. Right, so that's a bit of a subtlety. This is only intermediate vertices, so you could still go from I to j via a single edge. That will cost Aij. If there is an edge, infinity if there isn't one, but that is Aij. So, okay. That gets us started. And then we want a recurrence. And the recurrence is, well, maybe you get away with all the vertices that you had before. So if you want to know paths that use 1 up to k, maybe I just use 1 up to k minus 1. Could try that. Or you could try using k. So either you use k or you don't. If you don't, it's got to be this. If you do, then you've got to go to k. So why not go to k at the end? So you go from I to k using the previous vertices. Obviously, you don't want to repeat k in there. And then you go from k to j somehow using vertices that are not k. This should be pretty intuitive. Again, I can draw a picture. So either you never go to k, and that's this wiggly line. You go from I to j using things only 1 up to k minus 1. In other words, here we have to use 1 up to k, so this just means don't use k. So that's this thing. Or you use k somewhere in the middle there. Okay? It's got to be one of the two. And in this case, you go from I to k using only smaller vertices because you don't want to repeat k. And here you go from k to j using only smaller labeled vertices. So every path is one of the two. So we take the shortest of these two subproblems. That's the answer. So now we have a min of 2 things. This takes a constant time to compute. So we get a cubic algorithm. So let me write it down. So this is the Floyd-Warshall algorithm. You give it, write the name again. You give it a matrix A. That's all it really needs to know. Encodes everything. You copy C to A. That's the warm-up, right? At time 0, C equals A. And then you just have these three loops. For every value of k, for every value of I, and for every value of j, you'd compute that min. And if you think about it a little bit, that min is a relaxation. Surprise, surprise. So that is the Floyd-Warshall algorithm. And the running time is clearly n cubed. 3 nested loops, constant time inside. So we're finally getting something that is never worse than Bellman-Ford. In the sparse case, it's the same. In anything denser, if a number of edges is superlinear, this is strictly better than Bellman-Ford. And it's better than everything we've seen so far for all pair shortest paths. And this handles negative weights. Very simple algorithm, even simpler than the one before. It's just relaxation within 3 loops. What more could you ask for? You check that this isn't indeed what the min we're computing here, except that the superscripts are omitted. That's, again, a bit of a... I'm hand-waving a bit. It's okay to omit subscripts because that can only mean that you're doing more relaxations than you should be. Doing more relaxations can never hurt you. In particular, we do all the ones that we have to. Therefore, we find the shortest path weights. And again, here we're assuming that there's no negative weight cycles. Shouldn't be hard to find them, but you have to think about that a little bit. Okay, you could run another round of Bellman-Ford, see if it relaxes any new edges again. For example, I think there's no nifty trick for that version. Okay, and we're going to cover, that's our second algorithm for all pairs shortest paths. Before we go on to the third algorithm, which is going to be the cleverest of them all, the one ring to rule them all, to switch trilogies. We're going to take a little bit of a diversion, side story, whatever, and talk about transitive closure briefly. This is just a good thing to know about, and it relates to the algorithms we've seen so far. So here's a transitive closure problem. I give you a directed graph, and for all pair vertices I and j, I want to compute this number. It's 1 if there's a path from I to j. From I to j. Okay, and it's 0 otherwise. Okay, this is sort of like a boring adjacency matrix with no weights, except it's about paths instead of being about edges. Okay, so how could I compute this? That's very simple. How should I compute this is called this gives me a graph in some sense. This is adjacency matrix of a new graph called the transitive closure of my input graph. So, breadth first search. Yeah, good. So, all I need to do is find shortest paths, and if the weights come out infinity, then there's no path. If it's less than infinity, then there's a path. And so here, so you're saying maybe here I don't care about the weights, so I could run breadth first search n times, and that will work indeed. So if we do b times bfs, so it's maybe weird that I'm covering it here in the middle, but it's just an interlude. So we have then something like v times e. Okay, but you could run any of these algorithms. You could take Floyd-Warshall, for example. Why not? Okay, then it would just v cubed. You could run any of these algorithms, and with weights of 1 or 0 and just check whether the values are infinity or not. So, I mean, Tij equals 0 if and only if the shortest path weight from I to j is infinity. So just solve this. This is an easier problem than shortest paths. It is, in fact, strictly easier in a certain sense, because what's going on with transitive closure, and I just want to mention this out of interest, because transitive closure is a useful thing to know about. Essentially, what we are doing, and get this right, is using a different set of operators. We're using or and in logical or and, instead of min and plus. Okay, because we want to know, if you think about a relaxation in some sense, maybe I should think about it in terms of this min. So instead of, if I want to know, is there a path from I to j that uses vertices labeled 1 through k in the middle? Well, either there is a path that doesn't use the vertex k, or there is a path that uses k, and then it would have to look like that. Okay, so there would have to be a path here, and there would have to be a path there. So the min and plus get replaced with or and and. And if you remember, this used to be plus and this used to be product in the matrix world. So plus is now like or, and multiply is now like and, which sounds very good, right? Plus does feel like or, and multiply does feel like and if you live in a 0-1 world. So in fact, this is it's not quite the field Z mod 2, but this is a good, nice field to work in. This is the Boolean world. So I'll just write bool. Okay, good old Boole knows all about this. It's like his master's thesis, I think, talking about Boolean algebra. And this actually means that you can use fast matrix multiply. You can use Strasson's algorithm and the fancier algorithms, and you can compute the transitive closure in subcubic time. So this is subcubic if the edges are sparse, but it's cubic in the worst case if there are lots of edges. This is cubic. You can actually do better using Strasson. So I'll just say you can do it. No details here. I think it should be, well, so in fact there's a theorem, this is probably not in the textbook, but there's a theorem that says transitive closure is just as hard as matrix multiply. Okay, they're equivalent. The running times are the same. We don't know how long it takes to do a matrix multiply over a field. It's somewhere between n squared and n to the 2.3. And whatever the answer is, same for transitive closure. Okay, there's the interlude. And that's where we actually get to use Strasson and friends. Remember, Strasson was the n to the log base 2 of 7 algorithm. Remember that, especially on the final. Those are the things you should have at the tip of your tongue. Okay, the last algorithm we're going to cover is really going to build on what we saw last time, Johnson's algorithm. And I've lost some of the running times here, but when we had unweighted graphs, we could do all pairs really fast, just as fast as one single source Bellman-Ford. That's kind of nifty. We don't know how to improve Bellman-Ford in the single source case. So we can't really hope to get anything better than V times E. And if you remember running V times Dijkstra was about the same. So just put this in a recall bubble here. V times Dijkstra would give us V times E plus V squared log V. And if you ignore that log factor, this is just VE. Okay, so this was really good. Dijkstra was great, and that was for non-negative edge weights. So with negative edge weights, somehow we'd like to get the same running time. Now, how might I get the same running time? Well, it'd be really nice if I could use Dijkstra. Of course, Dijkstra doesn't work with negative weights. So what could I do? What would I hope to do? What could I hope to do? Suppose I want, in the middle of the algorithm, it says, run Dijkstra n times. then what should I do to prepare for that?
Make all the weights positive.
Make all the weights positive or non-negative, yeah. Why not, right? Well, we're being wishful thinking. That's what we'll do. So this is called graph reweighting. And what's cool is we actually already know how to do it. We just don't know that we know how to do it. But I know that we know how to do it. You don't yet know that we know that I know that we know how to do it. Okay. So, turns out you can reweight the vertices. So at the end of the last class, someone asked me, can you just add the same weight to all the edges? That doesn't work. Not quite, because some different paths have different numbers of edges. What we're going to do is add a particular weight to each vertex. What does that mean? Well, because we really only have weights on the edges. Here's what we'll do. We'll reweight each edge. So UV, let's say, I'm going to go back into graph speak instead of matrix speak. UV instead of I and J. And we'll call this modified weight W sub H. H is our function, gives us a number for every vertex. And it's just going to be the old weight of that edge plus the weight of the start vertex minus the weight of the terminating vertex. I'm sure these have good names. One of these is the head and the other is the tail, but I can never remember which. Okay, so we've directed edge UV, just add one of them, subtract the other. And it's a directed edge, so that's a consistent definition. Okay, so that's called reweighting. Now, this is actually a theorem. If you do this, then, let's say for any vertices U and V in the graph, for any two vertices, all paths from U to V have the same weight as they did before. Well, not quite. They have the same reweighting. So if you look at all the different paths and you see, well, what's the difference between VH, let's say delta, which is the old shortest paths, and delta sub H, which is shortest path weights according to this new weight function, then that difference is the same. So we'll say that all these paths are reweighted by the same amount. Okay, this is actually a statement about all paths, not just shortest paths. But there we go. Okay. So how many people is this obvious already? A few. Yeah, it is. And what's the one word? Okay, it's maybe not that obvious. But. All right, shout out the word when you figure it out. And meanwhile, I'll write this rather verbose proof. There's a one-word proof. Still waiting. So let's just take one of these paths that starts at U and ends at V. Take any path. We're just going to see what its new weight is relative to its old weight. And so let's just write out W sub H of the path, which we define in the usual way as the sum over all edges of the weight of the new weight of the edge from VI to VI plus 1. You have the word? No? Tough puzzle then. Okay. So that's the definition of the weight of a path. And then we know this thing is just W of VI plus 1. Get it right. Plus the weight of the first vertex, plus the reweighting of VI, minus the reweighting of VI plus 1. This is all in parentheses. It's all summed over I. Now I need the magic word. Telescopes. Yeah, good. Now this is obvious. Each of these telescopes with an extra previous, except the very beginning and the very end. So this is the sum of these weights of edges. But then outside the sum, we have plus h of v1 and minus h of vk. Okay, because those guys don't quite cancel. We're not looking at a cycle, just a path. And this thing is just w of the path, as this is the normal weight of the path. And so the change, the difference between wh of p and w of p is this thing, which is just h of u minus h of v. And the point is that's the same. As long as you fix the endpoints u and v of the shortest path, you're changing this path weight by the same thing. For all paths, this was for any path from u to v. And that proves the theorem. So the one word here was telescopes. These change in weights telescope over any path. Therefore, if we want to find shortest paths, you just find the shortest paths in this reweighted version, and then you just change it by this one amount. You subtract off this amount instead of adding it. That will give you the shortest path weight in the original weights. Okay. So this is a tool. We now know how to change weights in the graph. But what we really want is to change weights in the graph so that the weights all come out non-negative. Okay, how do we do that? Why in the world would there be a function h that makes all the edge weights non-negative? Doesn't make sense. Turns out we already know. So, I should write down this consequence. Get this in the right order. So, in particular, the shortest path changes by this amount. And if you want to know this value, you just move this stuff to the other side. So if we can compute delta sub h, then we can compute delta. That's the consequence here. How many people here pronounce this word corollary? Okay. And how many people pronounce it corollary? Yeah. We're alone, Canal. Usually I get at least one other student, and they're usually Canadian, I think that's or British or something. I think that's the accent. So I always avoid pronouncing this word unless I really think it's corollary. Yeah, okay. Get it right. I at least say Z, not Z. All right. Here we go. So what we want to do is find one of these functions. Let's just write down what we could hope to have. We want to find a reweighting function h assigns the weight to each vertex such that w sub h of uv is non-negative. That would be great for all edges. All uv in E. Okay, then we could run Dijkstra. Could run Dijkstra, get the delta h's, and then just undo the reweighting and get what we want. And that is Johnson's algorithm. The claim is that this is always possible. Okay, why should it always be possible? Well, let's look at this constraint. W sub h of uv is that. So it's w of uv plus h of u minus h of v should be non-negative. Let me rewrite this a little bit. Let's do what I want. Sure. I'm going to put these guys over here. That will be the right thing. H of v minus h of u is less than or equal to w of uv. Does that look familiar? Did I get it right? Should be right. Anyone seen that inequality before? Yeah, yes, correct answer. Okay. Where? In a previous lecture. In the previous lecture. What is this called? If I replace h with x. Charles knows. Good. Anyone else remember all the way back to episode 2? I know there was a weekend. What's this operator called? Not subtraction, but I think I heard it. Oh, man. All right, I'll tell you. It's a difference constraint, right? This is the difference operator. Okay. So our good friend difference constraints. So this is what we want to satisfy. We have a system of difference constraints. H of E minus H of U should be, we want to find these are our unknowns, subject to these constraints. We're given the W's. Now, we know when these difference constraints are satisfiable. Can someone tell me when these constraints are satisfiable? We know exactly when. Randy said a difference constraints. Got to remember the math. Terminology I can understand. It's hard to remember. Hard to remember words. Unless you're a linguist. Perhaps. So when is the system of difference constraints satisfiable? All right, you should definitely.
Constraint graph has
very
no
good.
negative. Has no negative.
Yes, very good. Someone brought their lecture notes. When the constraint graph has no negative weight cycles. Good, thank you. Now, what is the constraint graph? Uh-oh. Okay, this has a one-letter answer. More or less. I'll accept the one-letter answer. What, A? A, close, G. Yeah, I mean, same thing. Yeah, so the constraint graph is essentially G. Actually, it is G. Constraint graph is G. Good. And we prove this by adding a new source vertex and connecting that to everyone. But that's sort of beside the point. That was in order to actually satisfy them. But this is our characterization. So, well, if we assume that there are no negative weight cycles in our graph, which we've been doing all the time, then we know that this thing is satisfiable. Therefore, there is an assignment of this H's. There's a reweighting that makes all the weights non-negative. Then we can run Dijkstra. We're done. Isn't that cool? And how do we satisfy these constraints? We know how to do that with one run of Bellman-Ford, which costs order VE, which is less than V times Dijkstra. So that's it. Write down the details somewhere. So this is Johnson's algorithm. This is the fanciest of them all. It'll be our fastest. All pairs shortest path algorithm. So, claim is we can find a function h from v to r such that the modified weight of every edge is non-negative for every edge uv in our graph. And we do that using Bellman-Ford to solve the difference constraints. These were exactly the difference constraints that we were born to solve, that we learned to solve last time. The graphs here are corresponding exactly, if you look back at the definition. Or Bellman-Ford will tell us that there's a negative weight cycle. Okay, great. So it's not that we really have to assume that there's no negative weight cycle. We'll get to know. And if you're fancy, you could actually figure out the minus infinities from this. But at this point, I just want to think about the case where there is no negative weight cycle. But if there is, we can find out that it exists and then just tell the user. Okay, and then we'd stop. Otherwise, there is no negative weight cycle. Therefore, there is an assignment that gives us non-negative edge weights. So we just use it. We use it to run Dijkstra. So step 2 is, I should say the running time of all this is V times E. So we're just running Bellman-Ford on exactly the input graph, plus we add a source. If you recall, to solve a set of difference constraints, you add a source vertex S connected to everyone at weight 0. Run Bellman-Ford from there. Because we don't have a source here. We just have a graph. We want to know all pairs. So this you can use to find whether there's negative weight cycle anywhere, or we get this magic assignment. So now WH is non-negative, so we can run Dijkstra on WH. Let's say using WH. So you compute WH, that takes linear time, and we run Dijkstra from each possible source. So I write this out explicitly. We've had this in our mind several times, but when we said n times Dijkstra or n times BFS, here it is. We want to compute delta sub h now of uv for all v, and we do this separately for all u. And so the running time here is VE plus V squared log V. This is just V times the running time of Dijkstra, which is E plus V log V. Okay, it happens that this term is the same as this one, which is nice because that means step 1 costs us nothing asymptotically. Okay, and then last step is, well, now we know delta H. We just need to compute delta. So for each pair of vertices, call it UV, we just compute what the original weights would be, so what delta of UV is, and we can do that using this corollary. It's just delta sub H of UV minus H of U plus H of V. If I got the signs right. Yep. So this takes V squared time, also dwarfed by the running time of Dijkstra. So the overall running time of Johnson's algorithm is just the running time of step 2, running Dijkstra n times. Which is pretty cool. When it comes to single source shortest paths, Bellman-Ford is the best thing for general weights. Dijkstra is the best thing for non-negative weights. But for all pair shortest paths, we can skirt the whole negative weight issue by using this magic we saw from Bellman-Ford. But now running Dijkstra n times, which is still the best thing we know how to do pretty much for the all pairs non-negative weights, now we can do it for general weights too. And it's a pretty nice combination of all the techniques we've seen in the trilogy. And along the way, we saw lots of dynamic programming, which is always good practice. Any questions? This is the last new content lecture before the quiz. On Wednesday will be quiz review, if I recall correctly. And then it's Thanksgiving, so there's no recitation. And the quiz starts on Monday, so study up. See you then.